Hello all, welcome to the episode 34 in hexadecimal of Debugging TV Frames program. You can type your questions during this episode. If I can't answer particular questions now, I then post answers on the website debugging.tv. We continue with Android platform. This episode is about GDB debugging, code dump analysis, and some memory analysis patterns. There are two ways to perform GDB debugging using a remote server or directly from an Android device. I chose the second way. I'm grateful to Dan Drown, whose article referenced on this slide prompted me to evaluate that second way. First, we need to set up an environment. I already did that before. We need a rooted device, so we are able to become a root and attach GDB to running processes. And we view results of ADB Android Debug Bridge. Apps were compiled and downloaded via Eclipse and Android SDK, but for demonstrations here I run them directly from the device because I already downloaded them. So how to root device, it's up to you. You find lots of methods. I can't recommend any particular, just don't want if anything goes wrong with your device, so I shouldn't be blamed. So let's continue. So now with ADB session we start. Now I show you all this in action. I use a real device connected to this computer, and we use one app we discussed in the previous episode. It is called Jing Thread. If you watch the previous episode, you probably remember it. So I have already a console. So let's start ADB, shell, and because the device is rooted, I can become a super user. And let's see what processes are running. What I do, I start a Jing Thread up on device, and if I repeat PS, we should see that try to highlight that, so you see that in yellow I highlight. There's process ID. Disappeared. So remember, I use also command ps-t and if we look at Jing Thread now, what we see actually in the output of that command, what we see the header has process ID, thread ID, application name, disappears, and if we go scroll down, what we see is that Jing Thread has this process ID, 26945. But all other threads seems to be different process IDs. All have the parent process ID. And this has major implication when we try to attach GDB. Because when we attach GDB to a process, you see only one thread. So you have to attach GDB to a particular thread you are interested in. So what I do now, I push the button, and there should be different thread appear. Spiking one. What you see indeed, there is a new thread appears that has the same parent process ID, with a different process ID, and it is spiking. So what we do now, the article referenced here shows you how to get already compiled GDB for Linux ARM. So I already did that. And I put it, what was in that article, the folder, data, local, P. Let's see, I think it's also bin. So here we have GDB, as you see. And what I do, if I attach GDB to any particular thread, for example, if we choose the main thread, 26, the main process, 26949.945, and examine stack trace, we see that it is waiting. In waiting functions, so let's quit and reattach to another thread. Let's say this one. So it is 26959. And if we examine this backtrace, we see also waiting kernel, waiting functions, waiting conditional variable, something like that. And so we quit again. And let's now attach to our spiking thread. This is again, I highlight this thread. It is 27267. 27267. And backtrace now shows some raw code. So let's examine instruction at program counter. So here we can't access memory. This sometimes happens. In some running instances you can, in some running instances you can't. But let's, for example, access another one, 5F. So basically, in some instances you can access, in some instances you can't. For example, in the one run that I did before this presentation, I was able to access, and you see that the code was not waiting. I'm doing some comparisons. So you see how you can examine spiking thread here. And now we try what we do now. We do another exercise, and so we quit. If we list what is here, we also see core dumps. Actually, 1 second. Let me reattach GDB. Again, so there's no such process. So let's run spiking thread again and see its process ID. It's 2A217. So let's attach to it. What you can do, you can also save a core dump. The gcore command, for example, that saves core dump, and sometimes you can even open it. So we quit. If you look at this folder, we see a code dump was created for this process ID. Actually, when I was using GDB, it code dumped as well. So you see there is code.gdb file. So let's open it. So we specify exe as GDB and core as core.gdb. And we see what happened. We see backtrace. Let's dump instruction at program counter. You see also there was segmentation fault message. Program terminated with signal. So we now examine this program counter. And what we see, what happens is that the value of R0 register, the least significant byte, because this is sort of byte instruction, is moved at address that is located in R1 register plus 0 offset. So basically, we need to see if this address is valid or not, and what I use the info R, and this register dump shows that R1 contains dead bad address, non-accessible. So indeed we have here an instance of so-called invalid pointer pattern. So here's the output from one of the previous runs, but because we analyze the code dump here, the address is the same, of course. So this is all I wanted to show you. And finally, this is the usual add slide of forthcoming training sessions and free webinars. In addition to existing training, we are planning accelerated Linux code dump analysis based on ARM platforms in December. Let's see how it goes. It's not yet announced officially, and further details probably will be known in October or late. And so thank you for watching this episode. Please later check out the slides and recorded video from debugging.tv. The next episode should be on the 4th of November. Due to current workload and the forthcoming training preparation and sessions, the next episode number will be 1A in hexadecimal, as we found that we missed some numbers when we sequentially numbered our episode. So again, thank you for watching and listening, and see you all in November. Thank you. Bye-bye.